When a charged particle moves through a magnetic field, it experiences a force. Now, even when a non-charged object moves through a magnetic field, that non-charged object is usually made of charged particles, and so those individual charged particles will experience a force. So consider a chunk of metal flying through a magnetic field. As long as it's not flying parallel to that magnetic field, the electrons will experience a force and the protons will experience a force. If the chunk of metal does not have a net charge, then the force on the electrons will completely cancel out the force on the protons. But that force will still be there. Now, in general, protons don't move through an object, but electrons do. So in this chunk of metal, all of the electrons will be pushed to one side. Or rather, not all of them, because once some electrons start pushing up to one side, you start to build up a charge on that side, and that will repel other electrons. So only some electrons will move up to that one side. Now, I want you to consider this image. Imagine that all of these black lines are some kind of conducting metal. This line right here is a long chunk of metal that is moving through a magnetic field. This magnetic field is going into the page. So if we use our right-hand rule, motion to the left, so our thumb points to the left, magnetic field into the page, so our fingers are into the page, we see an upward force. Now, in reality, the force is on the electrons, which push the electrons downward, but when talking about current, we can pretend that there are positive charges moving around. And so the current gets pushed upward. Now, unlike our previous example, the charge doesn't just build up on the end. Rather, it can go through this whole loop of wire. Now consider, in this bar, the charge is being pushed upward. But on these bars, the charge isn't being pushed by the magnetic force, just by the fact that these charges are being pushed and they're moving out of the way. This is driving current. Now, when we talked about current and circuits, what drove current? Well, there was some voltage source. However, because of the details in how we define things, we can't call this voltage. So we're going to call it something. That is similar to voltage with slight changes in how we define it. We are going to call it the electromotive force. And we're going to treat it like voltage. So let's do some math. The force on a charged particle is equal to Q times V times B, assuming everything is perpendicular. Well, the work done by this force is equal to force times distance, again, assuming that force and distance are in the same direction. So in this bar right here, B is into the page, V is to the right, the force is upward, and the length of this bar is upward. So that's all working. So let's go ahead and replace this force with this force that we had right here, and we see that the work done is equal to Q times VBD. Well, since we're going to be using this electromotive force to replace voltage, or to supplement voltage, let's go ahead and say, we say that work is equal to charge times voltage before, so now we're going to say work is equal to charge times electromotive force. We can see in this equation, if the work is equal to charge times electromotive force, the electromotive force is equal to V times B times D. Now, I want to ask you a question to think about. What's the difference between an object moving through a magnetic field and a magnetic field moving past an object? In observation, none, because we can't decide that one thing's at rest, or rather, we do. We decide that it's at rest. There's no inherent at-restness to the universe. So, mathematically speaking, they should be the same thing. So, this bar is moving past these magnetic field lines, but if these magnetic field lines were going to the left, you should get the same thing. Except now there is a difference, because if they're moving to the left past this bar, they might also be moving to the left past this bar. So both of these bars would experience an electromotive force upward, which means no current. All right, what if the magnetic field is moving to the left here, but not moving here? On the one hand, yes, that should get back to our position of it does create a current, it does create this electromotive force which drives current. But on the other hand, we can see that if the magnetic field lines are moving to the left here and not moving to the left here, they'll start crowding into this area. And there we start to see a bit of a more elegant way of describing this. You see, if we take the quantity of magnetic field times this area, and magnetic field is represented by how dense these field lines are, then the more field lines there are in there, the more there is magnetic field times area. And in both of these scenarios, we are increasing the amount of magnetic field lines inside this loop. The first way by moving this bar to the right, expanding its area, and in the second way by moving the magnetic field lines in and increasing the strength of the magnetic field. So let's make this formal. Let's define this quantity right here, called the magnetic flux. Now, we saw electric flux when we were talking about Gauss's law. Electric flux, remember, was electric field times area. So magnetic flux is similar. Magnetic flux is magnetic field times area. And we can, with a bit of math, we can see that the electromotive force is equal to the derivative of this magnetic flux with respect to time. There's a negative sign. I'll get into that in a few minutes. So magnetic flux is equal to B dot A. That dot product, again, depends on direction. In this example, the area is, this rectangle is flat on the plane, and the magnetic field is going out of the plane. By convention, the direction of the area is normal to its surface. So in this case, the area and the magnetic field are going in the same direction. But what if we turned it? What if we rotated the magnetic field so the magnetic field was pointed straight up? Well, if the magnetic field was pointed straight up, then this bar would still experience some force on its charge, but thumb to the right, fingers pointing up, the force would be out of the page. So the electrons would be pushed, but they wouldn't actually loop. So the alignment of the loop and the magnetic field also matters. Now, magnetic flux is B dot A, which means we could also write it as B times A times the sine of the angle between them. And the electromotive flux depends on the derivative of this. The electromotive force depends on the derivative of this flux. Since this flux is the product of three terms, we can go ahead and break out our product rule, remember that, and say that the derivative of flux is equal to the derivative of the first times the second two, plus the derivative of the first and last times the derivative of the second one, plus the first and second one times the derivative of the last. One more thing, we're going to have to chain rule this now. Sine of theta is not explicitly a function of t, but if it were rotating, then we could say it's rotating at a constant angular rate omega, and say that this derivative is then omega times cosine of theta. Basically, what this means is that there are three ways we can create electromotive force. We can change the magnitude of the magnetic field. We can change the area, or we can change the alignment of the magnetic field and the area. As an aside, most power generation done today is done by taking a coil of wire and spinning it in a magnetic field, or spinning a magnet near a bunch of coils of wire. That would be this term right here. they're spinning, the angle is constantly changing. Now, I mentioned a coil of wire. Coils can have multiple loops. And if you take a single loop, it creates a certain electromagnetic or electromotive force. Consider if you take a bunch of batteries and hook them up together in series, the net voltage is the sum of their individual voltages. So you get a similar effect by having multiple loops in a magnetic field. Each loop provides a certain amount of electromotive force. So if there are n loops, we increase the electromotive force by a factor of n. Usually the way we account for this is by saying that the flux is actually N times B dot A. And we use this whenever we have a situation where there are multiple loops. Now, like I said, we are picking electromotive force to replace voltage. And we have to replace voltage because voltage is position dependent, but electromotive force is not. For our purposes, that doesn't matter too much, but it will become important if you get into this kind of stuff later on. But we can, all of our formulas related to voltage in circuits, we can replace with electromotive force. So we can have Ohm's law, V equals IR, becomes the induced current is equal to electromotive force divided by the net resistance. And you can also have power depends on electromotive force. P equals V squared over R becomes P equals EMF over R, or EMF squared over R. Apologies for the jump. I forgot I had this page in my first record. I promised that I would tell you about this minus sign. Well, that minus sign actually has its own name. It's called Lenz's law. Now, what is Lenz's law? Basically, Lenz's law is EMF always works against itself. So consider, this bar is moving to the right. It creates an electromotive force that induces a current around like this. Well, that current in this bar is also moving through a magnetic field, and is in a magnetic field, and so it experiences a force. So this time the current is going upward. The magnetic field is still going into the page, which means the force is to the left. The bar is going to the right, but the force is going to the left. If we were to reverse this, make the bar go to the left, we would also reverse the direction of current, which means we would reverse the direction of force. Lenz's law always tries to create an EMF that will oppose whatever it is that's creating that EMF. More generally, Lenz's law will create an induced current that tries to oppose how the flux changes.